Hello everyone. In this video, we're going to be solving a system of ordinary differential equations. X and y are both functions of t, and we're given this system. dx over dt is equal to yt, and dy over dt is equal to xt. And we're going to be solving for x and y in terms of t. And I'll be presenting multiple approaches. We're going to start with something that looks super basic, hopefully very straightforward and kind of obvious, hopefully. And then we'll go into more complicated approaches. So let's go ahead and first notice that we have the dx over dt and dy over dt in a very simple form. What does that mean? It just means that if we divide these equations side by side, then we're going to be getting dy over dx from here, which is a good thing, right? So you can find the relationship between x and y. So here's what we're going to do. We're going to go ahead and divide dy over dt by dx over dt. And by the chain rule, because 1 over dx over dt is dt over dx, so this is going to turn into dy over dx. And of course, if you divide, in other words, even though it's not very rigorous explanation, dt's cancel out, okay? So dy over dx becomes xt divided by yt. And of course, if t does not equal 0, you can also look at it separately. We get the following equation. We can go ahead and cancel them out. Now, this is a separable equation. Let's go ahead and put the y's together. We have y dy equals x dx. Beautiful. Now, this is really nice because we got rid of t. Good and bad, actually. So let's go ahead and integrate both sides, and then from here we're going to get y squared over 2 equals x squared over 2 plus some constant c1. Again, this is just any constant, c1, c2, just c, doesn't matter. But what I'd like to do is multiply everything by 2 to get rid of the fractions. Y squared equals x squared plus 2c1. And of course, 2c1 is a constant as well, so we can just replace it with c. So now we get the following interesting relationship. Y squared equals x squared plus c. What is that supposed to mean, right? Well, if you kind of put these two things together, this means y squared minus x squared. By the way, I think I want to approach it, well, actually, I think this is fine. So y squared minus x squared is equal to c, and this is a very important relationship. Now, notice that we don't have any t in this equation, right? But it relates x and y directly, which is an interesting thing. Now, here's what we're going to do. From here, we can actually isolate y squared and write it as y squared equals x squared plus c. And we can go ahead and consider the fact that x prime is equal to yt, right? And of course, from here, y can be written as plus minus the square root of x squared plus c. So we were able to get y in terms of x directly. And in this expression right here, we can replace y with this, right? Can't we? So that way, we're going to be able to express x prime in terms of x and t, which is nice. Now, let's replace y with this. And of course, we're going to have a t first plus minus t times the square root of x squared plus c, which replaces y from here. Okay? Awesome. And of course, the sign kind of depends on the initial conditions, but we can kind of ignore the minus sign and just maybe proceed with the plus sign, okay? So let's just say that, okay, I want to take x prime equals t times the square root of x squared plus c. And the other one is very, very similar, okay? Awesome. And guess what? This is a separable ordinary differential equation. Isn't that cool? So x prime, first of all, is dx over dt. That equals t times the square root of x squared plus c. And let's go ahead and bring the x term on the left-hand side. We get dx over square root of x squared plus c equals t dt. Awesome. Now, we were able to get something we can easily integrate. But when you integrate, what happens? Let's go ahead and take a look, right? When we integrate both sides, On the left-hand side, we're going to be getting, and definitely this is something you can do with some type of substitution. For example, you can replace x with the square root of c times tangent t. Actually, t is not a good choice. Let's say theta. And then, of course, from here you find dx, so on and so forth. But there's also a formula which is commonly used, which is the inverse hyperbolic sine. Or you can say arc sine hyperbolic. I'm not sure how you read it, but this integral right here is equal to the r sine, not arc sine, r sine hyperbolic. And this is going to be x divided by the square root of c. Of course, we kind of need to correct it because originally, it's supposed to be the square root of x squared plus 1. Of course, I'm assuming that c is greater than 0 in this case. What about the right-hand side? The right-hand side is actually pretty easy. You can just integrate it with respect to t squared divided by 2, and let's just go ahead and add c sub 2 here, because remember we used c sub 1 before. So from here, we can kind of put these two things together, r sine h of x over the square root of c, which is the integral from the left-hand side, equals t squared over 2 plus c2. And now we're going to go ahead and actually sine hyperbolic both sides, and then that'll isolate x over square root of c. So if we apply sine hyperbolic on both sides, it's going to look like this. Okay, you're going to get t squared over 2 plus c2. And then if you multiply both sides by root c, you're going to be able to get x in terms of t, which is huge. Isn't that cool? Now we get x in terms of... So we basically solve for x. But guess what? We also have a formula for y, right? So we know that y, and we know that from here, remember? Y is equal to this. But remember, we took the one with the plus sign. So y is equal to square root of x squared plus c. So if you just consider x squared is just going to be, this expression from here, square root of c times sine hyperbolic, t squared over 2 plus c2, and you're supposed to square the whole thing, right? This is x, square it, and then you're going to add c to it, and then square root, so you can't really simplify it anymore. But that's going to be the y value in this expression. So what happens here is when we found that y squared minus x squared is equal to a constant, where did we find that? Right here. That just means that y squared minus x squared is an invariant, okay? Which means it's something that is kind of like a constant. Now, we were basically able to solve for y, as you can see here, x, and then we found y in terms of x, so that pretty much concludes the solution. But there's another way we can approach this problem. Let's go ahead and call that second method. Second method is kind of like, I think, more cumbersome, definitely more complicated, but I still want to share with you maybe just a brief intro to the method and how that works. So remember, our system is x prime equals ty and y prime equals tx, right? Now, here's what we're going to do. We're going to go ahead and differentiate both sides on the first equation. If you differentiate x prime, you get x double prime. And on the right-hand side, you have to differentiate ty, but y is a function of t. So ty is a function of t, so we have to use the product rule. The derivative of t, which is 1, multiplied by y, plus the derivative of y multiplied by t. So that's what you get. In other words, y plus y prime t gives you the second derivative. Now, you can actually go ahead and replace y prime with xt, because remember, that was given in the original system. So from here, x double prime equals y plus xt multiplied by t. So we're replacing y prime with xt. That's what we get. If you simplify, you get y plus xt squared. Awesome, right? Now, we're going to do one more thing. So let's go ahead and actually put the t squared x on the left-hand side, because it contains x, so it should be on the left-hand side. And let's just isolate y for now. So what is next, right? Well, we know that x prime is equal to ty, right? But we don't have x prime in this equation, and we do need actually y from here. So since x prime is equal to yt, from here y becomes x prime divided by t. So we're using substitution a lot. Isn't that fun? We're going to go ahead and take this and replace this y with that. X double prime minus t squared x equals y, which is x prime divided by t. And guess what happens? Everything is expressed in terms of x. Well, it's not a constant coefficient equation, but it can still be solved. And guess what? This is just going to be a second order ODE, which is a differential equation, ordinary differential equation. All right? So let's go ahead and multiply everything by t. We get t x double prime minus t cubed x equals x prime. Now let's go ahead and put everything on the same side. T x double prime minus x prime minus t cubed x equals 0. So we kind of have something like some function times x double prime plus some function times x prime plus some function times x, right? So we should be able to solve it somehow, don't you think? There should be a nice way to do it. Maybe, is it one of these special forms? Nope, it's not actually a special form because the problem is the powers of t do not really agree with the order of the term. So we're going to go ahead and do the following. We know that y squared minus x squared is equal to constant, right? Yeah? So we could also arrive, so since this is a constant, we're going to be using a special type of substitution. So if you do the following, you say, okay, x equals the square root of c multiplied by cosine hyperbolic u of t. U is a function of t, by the way. And for y, we're going to be doing the sine hyperbolic for the same function. And from here, if you evaluate the derivatives, okay, and plug them into the system like x prime equals ty, obviously you're going to have x prime from here, and you're going to have the y here. You're going to plug it in, and what you're going to be getting from there is basically, because the derivative of x prime is going to be square root of c multiplied by u prime times sine hyperbolic of ut. Why? Because by chain rule, we also have to differentiate the inside, which is the derivative of u. Great. Now, we could actually kind of, this is kind of too cumbersome. Let's just use u instead of that because we already know that u is a function of t in this case, right? Great. Now, if you go ahead and let's turn this into a u as well. So now, we're going to go ahead and substitute this. We know that x prime is ty, so square root of c times u prime times sine hyperbolic of u equals t times y, which is square root of c times sine hyperbolic of u. Guess what? That'll cancel out the sine hyperbolic and the square root. We're going to end up with something super nice. U prime equals t. Isn't that cool? Right? Okay. Of course, if you, and remember, u is a function of t. We said that, right? So now if you integrate both sides with respect to t, you're going to get t squared divided by 2 plus c sub 2 again. You can use any constant you want. It doesn't really matter. But again, we had assumed that x would be in this form and y would be in something similar. So now, since you already know u, you can go ahead and write x as square root of c multiplied by cosine hyperbolic of t squared over 2 plus c2. And for the y, you're going to write the same square root, but this time it's just going to be sine hyperbolic t squared over 2 plus c2. So inside they have the same thing, but one of them is cosine hyperbolic, the other one is sine hyperbolic. Make sense? I hope it does. Okay. So basically, you can, approach this problem in so many different ways. You can also use a different way to substitute, which I can tell you. Remember what we did? We took the equation x prime equals yt. We differentiated both sides. We got the second derivative, and then we substituted xt for y prime, sorry. And then we arrived at an equation, right? You can also use a different substitution, and that would look like this. X equals e to the power t squared over 2 multiplied by u. And again, u is a function of t. And if you go ahead and find the first derivative and the second derivative and plug in everything, trust me, it's going to be super cumbersome. But I'm going to skip some steps, and a lot of things are going to cancel out. And you're going to end up with something like this. U double prime plus 2t minus 1 over t all multiplied by u prime equals 0. And guess what? We can actually reduce the order of the derivative because we don't have u, we have u prime and u double prime. So if you set u prime equal to v, this equation is going to turn into v prime plus the 2t minus 1 over t expression multiplied by v equals 0. And guess what? This is separable. How do you separate that? You can first put everything on the right-hand side, like, negate it like this. And then you can divide both sides by v. v prime over v is equal to 1 over t minus 2t. And then you can go ahead and integrate both sides. V prime over v from chain rule, you'll remember, it's a derivative of ln v. So let's just write it as ln v. And this is just ln t, right? Minus t squared plus some constant. Let's just use t, okay? It doesn't matter. They're disposable. Now from here, of course, you're going to have to do some work. If you do e to the power both sides, then you should be getting something like c t e to the power negative t squared. But one thing you got to remember, this is v, and v is the derivative of u. So now we have u prime is equal to ct e to the power negative t squared. And now what are we going to do with this? We have to integrate both sides again. And it's easy because if you think about this by u substitution, not this u, but another u, you're going to get u equals negative c over 2 times e to the power negative t squared plus another constant. Oops, I meant this constant like here. Let's call that c2. Now, this is u. And if you remember, we had assumed that x is going to be in this form. So we can go ahead and substitute that. And that'll give us the answer for x. So x is going to look like something like this. E to the power t squared over 2 multiplied by c2 minus, I'm just reversing, or I mean switching sides so that we can write the positive term first. And then if you go ahead and actually distribute this, you're going to get something like c2 e to the power t squared over 2. And then minus, when you multiply these two things, it's going to give you t squared over 2 again, but with a minus sign because this is bigger. So you're going to get c divided by 2, but you can just call that c1 and e to the power and negative t squared over 2. And of course, the constant can absorb the minus sign, so you can go ahead and write it like this. And of course, from x prime equals yt, if you isolate y again like this and divide the whole expression by t, you're going to get the answer for y. So we basically get the final solution, but guess what? Isn't this very different from what we found? That's for you to find out why these results are very much different looking. Let me give you a clue. All right? And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.